I am Professor J. N. Mandal, Department of Civil Engineering, IIT Bombay. I earlier explained how to determine the flexural strength of different types of EPS geofoam material. I will show you what are the properties of flexural strength of EPS geofoam can be determined and how you can calculate. I will show particularly one type of EPS geofoam material densities and how we have calculated. So, in this table that some specimen calculation for the determination of the flexural strength of geofoam. So, density of geofoam 15, 20, 22 and 30. So, maximum load at failure which we obtained for 15 density it is 25 Newton, for 20 density of EPS geofoam 34.2 and 22 density of EPS geofoam 40.1 and 30 density of EPS geofoam 46.1. This is the maximum load at failure. So, from this we have calculated the flexural strength for 15 kg per meter cube EPS density, the flexural strength of EPS geofoam 149.9, for 20 density 211.3 kilopascal, for 22 density it is 240.6 kilopascal flexural strength of EPS geofoam, and for 30 EPS density the flexural strength is 277.0 kilopascal. You can also measure the deformation at the center for 15 density 0.02541 meter, for 20 density it is 0.3313 meter, and for 22 density it is 0.03811 meter, and for 30 density 0.04687. And you can determine what will be the maximum strain millimeter per millimeter, that is for 15 density 0.06, for 20 density 0.08, for 22 density 0.09 and for 30 density 0.11. From this data you can also determine what will be the moment of inertia, that is m to the power 4. For 20 density 1.3 into 10 to the power minus 7, for 20 density 0.08 1.3 into 10 to the power minus 7, and for 22 density it is 1.3 into 10 to the power minus 7, and for 30 density also 1.3 into 10 to the power minus 7. You can calculate also the modulus of elasticity of EPS geofoam. For 15 density 2518.69 kilopascal, for 20 density 2584.87 kilopascal, and for 22 density it is 2815.95, and for 30 density 3088.52 kilopascal. So, for the different density of the EPS geofoam, you see that modulus value also is increasing, and this flexural strength is very important in various application of civil engineering project. And I will show you for a particular density of EPS geofoam whose density is 25 kg per meter cube, and how we have calculated the value of the flexural strength, etc. So, we are considering that EPS geofoam density is, let us say, EPS geofoam whose geofoam density is 20 kg per meter cube. API density. Showing here. Let us consider the EPS geofoam density is 20 kg per meter cube. So, let us say from the testing result you obtain that P is equal to 0.0342 kilonewton. Okay. And length of the EPS geofoam material is 0.25 meter and B is equal to 0.1 meter and depth D is equal to 0.025 meter. So, from this data you can calculate what will be the flexural strength. So, flexural strength this will be equal to 3 into P 0.0342 into length 0.25, this divided by 2 into B 0.1 into D square, that means 0.025 this square. Here D is equal to if you can calculate this, then you can have the 211.3 kilopascal. So, flexural strength we calculate it 211.3 kilopascal. Now, D is equal to 0.03313, small d is equal to 0.025 meter and L is equal to 0.25 meter. So, you can determine from this data what will be the maximum strain. So, maximum let us say strain is equal to 6 into 0.03313 into 0.25, this divided by 0.25 square. This is 0.25 square. So, this will give the maximum strain value is 0.08 millimeter by millimeter. So, this is the maximum strain is this. So, what I showed you earlier in this table, you can see that flexural strength is 211.3 and the maximum strain is 0.08. That means here the flexural strength is 211.3 kilopascal and the maximum strain value here, maximum strain value is 0.08 millimeter per minute. Now, if B here is 0.1 meter and D is equal to 0.025 meter. So, you can calculate moment of inertia. Moment of moment of inertia, that is I will be equal to 0.1, you know, B d to the power q, that means 0.025 q, this divided by 12. Okay. So, this moment of inertia, if you calculate, we can have 1.3 into 10 to the power minus 7 meter 4. So, you can calculate moment of inertia is equal to 1.3 into 10 to the power minus 7 meter 4. Now, next we will calculate this elastic modulus. So, for this, you know, P is equal to, you know, 0.0342 kilonewton, L is equal to 0.25 meter, and you know that I you know, that means 1.3 into 10 to the power minus 7 meter 4. So, you can calculate elastic modulus, elastic modulus that designated at E. E will be equal to 0.0342, that is P, into 0.25, this is Q, PL to the power Q, and this divided by 40 of 8 into 1.3 into 10 to the power minus 7 into your 0.03313. 0.03313. So, if you can calculate, you can have 2584.87, that is kilopascal. So, elastic modulus, this is 2584.87, that is kilopascal. So, you can calculate the moment of inertia, you can calculate the elastic modulus E. So, in this table also it is shown that you have calculated maximum strain 0.08, and this is the moment of inertia 1.3 into 10 to the minus 7 meter 4, and this is the modulus of elasticity 2584.87 kilopascal for a density of 20. So, here also we have calculated that moment of inertia is 1.3 10 to the minus 7, and elastic modulus value is 2584.87. So, this way you know the equation. So, you can calculate the moment of inertia and elastic modulus of EPS geofoam material. Now, I will discuss the flammability test on the expanded polystyrene material or EPS material as per the code specification IS 4671 1984. Because this material is combustible, so you cannot keep it on the open sunlight. You always prefer to cover with some the soil on the top of the EPS geofoam material. Even then, when if you stock any kind of the EPS geofoam material, you should always cover it. And sometimes if you know that when the EPS come in contact with the gasoline or acetone or the petrol or diesel, so it will destroy or it illuminating. So, here for this test, flammability test on expanded polystyrene, so main objective of this test to study self-extinguishing property of expanded polystyrene. So, this test classify the rigid cellular material into self-extinguishing and non-self-extinguishing type. The test specimen size, here you can see that test specimen size is about 200, from here to here is the 200 millimeter, and from here to here is 75 millimeter, and from here to here it is 50 millimeter. And sample size is from here to here it is 20, and from here to here it is the 15 millimeter. That means test specimen of size is 200 millimeter into 25 into 20 centimeter. So, this is the sample size. So, the testing procedure is that you clamp the specimen to a rigid support and place the burner at an angle of 45 degree and maintain the flame in contact with specimen until the specimen burn. Remove the flame immediately and specimen is classified as self-extinguishing if it does not burn beyond the second mark. I will show you the two marks and what parts of the mark it should go. Then you will be able to say that it is a self-extinguishing, and if beyond that, then the sample will not be considered. So, here in this figure you can see some EPA geofoam test specimen of flammability test. So, there are two lines has been drawn here. I will show you that what is the two line, and this is the defined types of the density of the EPA geofoam is shown here. It may be 15, 22, 20 and 30 density of EPA geofoam material. Now, how to perform the test and how to part this EPA geofoam material and what angle, and that part should go certain distance, not behind the certain distance. So, here I am showing that you can see here, and this is this specimen is tightening here, and this distance is the 50 millimeter and this is the 75 millimeter, and this sample is tightened. This sample is tightened. This is the word gauge around 1.25 centimeter, and this is making at an angle of 45 degree. And then you burn. You can see here, then light this EPA geofoam material and it is burning, and it should reach up to this, not behind that. If it is behind this mark, then this material will not be considered for self-extinguishment. So, this is the sample, this you can see this material is burning. This is the schematic representation and photograph of the flammability test for a particular density of the EPA geofoam material. I will show you that after this flame and how much it has reached and how it stopped the burning. If you can see the next slide here, this is the flammability test on EPS geofoam with the different density. This is 20, this is 22, this is 23 and this is 30 of density of EPA geofoam. And after the test you can find here, you can see that it reached up to this, not behind this. it is up to this. That means EPA geofoam showing self-extinguished characteristics. It goes here, not behind this. Next density you can see it reaches here, not behind this line. It reaches here, not behind this line. So these are the shown for defining density of the EPA geofoam and showing the self-extinguishing characteristics. So as the all geofoam sample do not burn this behind this second mark, which I have shown you, the second mark here is behind the second mark, as I have shown it in this figure, the geofoam was found to be self-extinguished style. So we have some idea that how to perform the test. This test is very simple, and you always keep it in mind that film parts should not go behind that second line, then it will not be the self-extinguished. Now flammability means this is a fire. So geofoam can be considered to combustible, so it should not expose to flame. As I told you, it should not expose to any flame, and it can be always covered with the backfill soil. Some geofoam also contain a flame retardant additive to reduce the risk of ignition from during the construction. So you know that how to perform this kind of the test. Apart from this kind of the flame test, we have the some other test which you call the thermal property or thermal resistance or thermal conductivity. Now this is important, that thermal resistance and thermal conductivity of the EPA geofoam material. In case of the refrigerator, or if you wanted to store the any kind of the food, and when the water level at a certain depth, so you have to construct a foundation or construct a house or a container in order that water level should not reach on the top of the refrigerator or the container. So there will be a difference in the temperature. So if the difference in the temperature, in the conventional method, most of the cases we use the gravel and the concrete, okay, as a thermal insulation. So now alternative to this system, and you can adopt the EPA geofoam material instead of the gravel, and you can observe that what will be the difference in the temperature, how much you can save the watt. That just I will show you with one of the example. But it just to know that thermal property, thermal resistance of the geofoam material. The thermal resistance is measured as per STM-C 303D 1622 or DIN, that is German specification 52612 or DIN 4108. And thermal resistance can be defined as the heat flow per unit width of geofoam. The unit of thermal resistance R is m degrees centigrade per watt. So as you have maybe studied it in the subject of physics. And similarly, what is thermal conductivity? That is designated at K. So geofoam has very good heat insulation property. So geofoam is poor heat conductor. As the air entrapped in it, the thermal conductivity can be defined as the rate of heat of flow in the material, that is designated at joule per second or the watt, and the unit K is watt per m degree centigrade. So I will just show you this one of the side, that what is the thermal conductivity K and thermal resistance R for various material. So, you can obtain that thermal conductivity of the different material, geofoam, concrete, brick, plaster, steel, iron and the water. So, this is the K thermal conductivity, these are the value is given, and this is the thermal resistance R for the different types of the material. You can observe here what is the thermal conductivity and thermal resistance for the geofoam and other material. I will just show you that one example, that how you can determine the thermal conductivity of a material. For example, you want to construct a house, okay, and here, and the lower part is the concrete, and this part is the gravel. Okay. So, alternative to this, you can construct the any kind of the house, let us say here, and this top part, let us say concrete, and bottom part is the geofoam material. So, let us say that building area is 30 centimeter into 30 meter into 20 meter, and thermal resistance of the concrete, let us say it is given, you can have from the table also 0.78 degree centimeter square, what is 300 millimeter rest on gravel or the concrete. Now, thermal resistance for the brick is 1.1 degree centigrade per meter square per watt. This is in the traditional system what we adopt. Alternatively, if you adopt the geofoam system, then thermal resistance of the geofoam or EPS geofoam, thermal resistance of EPS geofoam is 30 degree centimeter square by watt, and temperature between the ground and the basement is, let us say, 25 degree centigrade. Now, you have to find out what will be the difference in the temperature between the two systems. So, one system conventional, another system is the concrete geofoam material. If you adopt these two systems, you can calculate that what should be the temperature difference between these two systems. So, you know that equation for heat flow that is H is equal to AH into delta of T divided by R. So, delta, this is H is equal to heat flow, AH is equal to cross section area of the heat flow, and delta T is the different temperature across the material, and R is equal to thermal resistance. So, when you use the, let us say, brick or the gravel, when you use the gravel or the brick, that is the traditional method if you adopt, then heat flow H will be equal to AH into delta of T, this divided by R. That means AH is 30, that is area, H is 30 into 20 meter. So, this is 30 into 20 meter. That means this will be giving about 600 square meter. And R of concrete is 0.78 centimeter square per watt. and R of brick is 1.1 degree centimeter square per watt. So, you can calculate the H will be equal to 30 into 20 into 25. This divided by 0.78 plus 1.1. So, if you calculate, you can have the heat about 7978 watt. Whereas, if you use the geofoam material, okay, so let us say R of geofoam is equal to 30 degree centimeter square per watt. So, if you can calculate, the H will be equal to 30 into 20 into 25. So, this divided by plus 0.78 plus 30. So, if you can calculate, you can have 487 watt. So, when if you use geofoam 487 watt, when you use the conventional method, that heat generated is 7978. That means it is 16 times less when you use the geofoam material. So, you see from this example, if you use the expanded polystyrene geofoam material, that heat can be substantially decreased with respect to the conventional method. Thank you.